In this video, we're going to take a look at refraction terminology and do some practice problems involving refraction. So let's analyze this diagram over here. You can see there's two media. There's the first medium and the second medium. This could be air, this could be glass, doesn't really matter. The point is there's two different substances. The boundary between this substance and this substance is called the interface. So this might be the top of the water, for example, or top of the glass. The ray that when you start off in the first medium, that first ray you're starting with is called your incident ray because it's going to go into the second medium, so it's called the incident ray. And the ray that goes into the next medium and bends is called the refracted ray instead of the reflected ray because it's going through and refracting, not necessarily reflecting. Just like with mirrors and reflection, you can draw a normal that's 90 degrees between 90 degrees to the surface between the two media. And the reason you draw that normal is so you can measure angles. So the angle between the incident ray and the normal is called the angle of incidence. We call it theta 1 here instead of theta I, but you could also call it theta I. The angle between the refracted ray and the normal is called the angle of refraction, which we call theta 2 here instead of theta r because theta r represents the angle of reflection. Sometimes we call theta little r the angle of reflection and theta big R the angle of refraction, but to avoid confusion we're just going to use theta 1 and theta 2 in this situation. So we have our terminology understood. Now we're going to go use our terminology to do some problem solving and to learn how to predict the path of a refracted ray as it goes from one substance to another. This here is just an optional enrichment opportunity. You can watch a video about what's called Snell's law. And what Snell's law is essentially a mathematical way to determine the angle of refraction specifically. We're going to just predict the rough angle without actual numbers, but if you understand that well and you want to see how to use this formula, just watch this video quickly and you can do a few practice problems within the video to understand how to use Snell's law to find the angle of refraction, as long as you have the index of refraction for medium 1, medium 2, as well as the angle of incidence. All right, so when light goes from one substance to another, there's two things that can happen to it, or two main things that can happen to it. So here you can see the incident ray hits the surface and then goes into the next medium. And you'll see that it looks like that refracted ray bent away from the normal. So let's move this up here, get the pen on here. It looks like this refracted ray moved a little bit away from the normal. So this is our theta 2 and this is our theta 1. It looks like our theta 2 is larger than our theta 1, so we moved away from the normal. Whereas in this situation here, this was our theta 1, and this is our theta 2. So our theta 2 is smaller than our theta 1. That means that this refracted ray moved towards the normal. So the two things that can happen is a refracted ray moves towards normal. So this angle is smaller here, the refracted angle, the angle of refraction is smaller than the angle of incidence, or moves away from the normal. So the angle of refraction is larger than the angle of incidence. And so how does that happen? When do these situations happen? So for the case to move away from the normal, the way that would happen is when you're going from a slow medium, so in other words a high index of refraction, to a fast medium. So slow to fast, low index of refraction here. And so the trick for that is sonic farts a lot. S for slow, F for fast, and then a lot, A for away. So we can call that SFA, slow to fast, away from the normal. And the way to think about it is, if you look at this lawnmower over here, it's on the grass right now, and it's hard to push it on the grass because it's bumpy and there's grass in the way. As you go from the grass to the pavement, let's pretend this is our normal here, the dotted line, this wheel will hit the pavement before this wheel. So this wheel speeds up. and this one stays slow, and so it kind of drags the whole lawnmower a little bit in this direction, as opposed to continuing on that path this way. And so that's essentially what's happening here because of the change in the speed of light. It's not uniform across the whole wave. Now, in the case of the light ray moving towards the normal, well, we use the trick Fun Science Teacher, FST. So that happens when you start off in a fast medium, so one with a low N, and then you travel to a slow medium, one with a high N. And that causes the ray to move towards normal. So it's sort of like it's the opposite of what we saw up here. You start off on the pavement, and then as you go onto the grass, this wheel gets on the grass first, so it slows down before this side and drags the lawnmower this way, a little bit closer to the normal, rather than continuing down this path here. So it's the opposite situation. Again, that refraction is happening because the light ray changes its speed at different points as it enters the second medium. So you have to remember the tricks FST and SFA to make predictions about which way how your refracted ray will bend, away from the normal or towards the normal. Here we call theta r the angle of refraction, theta r, but this could also be theta 2, and this is theta 1, theta 2, and theta 1. All right, so we're going to do a couple practice problems here. I'm going to carry out 3 of them in this video, or 2 of them in this video, and you're going to try your own, and then I'll reveal the answers afterwards. So here's our question. In the diagrams below, determine which medium has light that travels the fastest and which medium has light that has the highest index of refraction, the top one or the bottom one. So this is, let's call this medium 1 and this medium 2. Let's examine what's happening to light. Here's our normal, and here's our refracted ray. And you can see clearly that this refracted ray has moved away from the normal compared to here. This angle is larger, so we moved away from the normal. This is our first medium here, because that's where light starts off. It's going this way. So if we're moving away from the normal, that's the SFA trick. Sonic farts a lot. So that means this must be the slow medium, and this must be the fast medium. And so this had the high N over here, and this one had the low N over here. You can try diagram B yourself, and I will take it up. So over here we have, this is medium 1 because it's where light starts off. This is medium 2 because it's where light ends up. You can see again that light has moved away from normal. So we once again have a situation that's SFA. But this time the slow is here, so slow, and fast is up here. So this has the high N, and this has the low N. You can try diagram C, D, and E, and you can reveal the answers as you go through this PowerPoint. But you can see for diagram C, the top has the fast light. And this makes sense. We're going towards the normal here. So we're looking at a fun science teacher. So fast to slow towards the normal. Here as well, you're looking at a fast to slow towards the normal. And here you're looking at a slow to fast away from the normal. And so that's how you would approach this type of problem, where you have everything filled out for you, but you just have to figure out where you have the slowest light, fastest light, and therefore where you have the highest N and the lowest N. All right, in this question, you're going to predict the path of light in the different circumstances provided. So you have 2 media, medium 1 and medium 2. In question A, we said that medium 1 has a higher refractive index than medium 2. So medium 1 has the high N, and medium 2 has the low N. So what this means is that this is medium 1, this is where light starts off. This is high N means slow, and medium 2 is low N means fast. So this is an SFA, sonic farts a lot situation. So you're going to want to draw a refracted ray that has a larger angle than the theta 1, that's farther away from this normal here. So something like this, where this is larger. This is theta 2, and the theta 2 is clearly larger than theta 1. It's farther away from the normal than theta 1 was. You don't have to know the exact angle, just make sure it looks larger. If we want to know the exact angle, we'd have to figure it out using Snell's law. All right, now part B, you can try it on your own and check your work. Medium 1 had a lower index of refraction than medium 2. So we're saying that medium 1 has a lower n, so this is the fast one, and medium 2 has a high n, so this is a slow one. So we're going fun science teacher, so towards the normal. So this is your theta 1, so you need to make sure that your theta 2 is smaller than your theta 1 because it's moving towards the normal. Like that. This is another type of problem that you can try out as well. So let's see the instructions here. For each diagram, draw the normal and then approximate refracted ray. Hint: for each problem, draw the normal and then estimate using SFA and FST. So let's start with this one here. So we have n is equal to 1 and n is equal to 1.3. This is our first medium over here. And we know this is the fast one, right? Because it has a lower n. And then over here, we have second medium, and we know this is a slow one because it has a higher n. So this is going to be a situation of fast to slow towards the normal. Problem is there's no normal in there yet, so you have to draw that in, and you basically draw it in where the light ray hits the surface. 90 degrees to that surface. And then you can draw in your refracted ray. So it should look something like this. You have fast to slow towards normal, so a little bit, and I'm not using a ruler here, but it should look closer to the normal than this over here. So normals are drawn in here. And the answers are shown there. So what you should do is you should try the problem out yourself first and then check your work to make sure you're on the right track. Again, follow the same model that we did in that question there. So basically this one here, we have a fast to slow towards the normal. So the angle looks smaller here. Over here we have a slow to fast. So we have a SFA, sonic farts a lot. So the angle you draw in should be larger. And again, we're just doing this more of a qualitative approach as opposed to a purely quantitative one where we know the number, because we're not using Snell's law right now. And then you can try this problem here. We have to draw a little bit more. So try it yourself, pause the video, and then check your work. So if the angle of incidence in material X is 50 degrees and the angle of refraction in material Y is 40 degrees, which medium does light move faster in? Which material is more optically dense? Answer it with a label diagram. When I say optically dense, that simply means which one has the higher N, which one is light that travels the slowest. So dense means a substance in which light travels slow. So try it out. So you would first draw that boundary. You would draw a normal. It says that the angle of incidence in material X is 50 degrees. So the angle of incidence is in material X over here. That's where you're starting off, and you can measure a 50-degree angle here. And then the angle of refraction in Y, you can measure that with a protractor, is 40 degrees. So it's a bit smaller. So this is theta 1, and this is theta 2. And so what we have is a situation where we moved towards the normal, T. So if we move towards the normal, that's a situation that's fun science teacher, FST. So this must have been the fast one, and this must have been the slow one. So that means that this would have been the higher N, and it would have been the more dense one here. And this would be the fast one. So So let's see our answer. So light moves faster in medium X. The light ray followed FST pattern. This means that the light traveled faster in the first medium X and slower in the second medium Y. So using our tricks, we're able to predict the density and speed of light in the different media based on the way light traveled from one to another. So in this video, we saw terminology for refraction. We saw how to predict the way in which light would refract either towards or away from the normal using some tricks. And we saw that the bending was because of the changing speed of light as it goes from one substance to another. In the next video, we're going to take a look at some applications of refraction that you would see in your everyday life.